So, hello everyone. I'm Inbal, Livni, Navon, and I'm going to talk about indistinguishable models of huge objects. This is a joint work with Omar Reingold and Lunja Hu, both from Stanford University. So, I'm going to start by some background. So, generative models in general is the idea we're trying to generate a distribution which is similar either to another distribution or to a specific object. And in this work, we only care about trying to imitate a specific object. So we have some object. You can think about it as a graph or a function. And we're trying to output a model that generates randomly some G prime that's going to be similar to the original object. And I'm going to talk later about what do I mean by similar. So we might have wanted to do a deterministic thing, but in most settings, this is impossible. So we want a model to randomly generate this. Now, setting of pseudo-randomness that was discussed quite a lot in this conference, we're trying to generate an object that seems like it is random by using a little bit of randomness. So if we think about our object as a graph, then random graph requires poly n random bits, and we might want to do only polylog n random bits and output a graph which seems like it is random. So in 2010, Goldwasser and Nissenbaum had this idea of trying to generate random-looking objects which are huge. So we can think about them like an exponentially sized graph. And we want to generate an exponentially sized graph that looks like a random graph. So if our pseudo-random generator, the algorithm that generates the graph, is polynomial, it can't really output an exponential sized graph. So what it does output is an implementation, which is like a small representation that can either output queries or give samples from these exponential sized objects. And what we're doing in this work, we're combining these two settings and we generalize it. And we try to have a generative model that is also in this huge object setting. So this is what we're trying to do. We have now a huge specific object. So we're trying to imitate a specific huge object and not a random object. But this is still huge, so we still need a small implementation. And in our case, the implementation is only going to output random samples and not to answer queries. So we want our implementation to be small. And we also want this implementation to be similar to the huge object we started with. So what do I mean by being similar? So in generative models, sometimes there are specific properties that we want to keep, maybe the degrees, maybe the edges across a cut, if this is a graph. But in order to talk about it in a formal way, in this work, we're using the language of outcome indistinguishability. So this was a formalization from the fairness literature by the work from Reingold, Rothblum, and Jona. And the idea is that, like in the pseudo-randomness setting, we have a distinguisher. It is an efficient randomized algorithm. It receives samples either from this G or from G prime. And then it can accept or reject. And we want it to accept with similar probability for our original object and for our generated object. And so normally, a distinguisher would check for a specific property. So if our object is a graph, it can be number of edges crossing a specific cut. So we have a collection of distinguishers, and we want to be indistinguishable with respect to any one of them. So this is our goal. Now, I've talked about what we want to achieve, but now how can we achieve that? So we have a specific object. We need to somehow learn this object to know how to generate something that is indistinguishable. So we need a learning algorithm. And this learning algorithm can also receive samples from our huge object, and it should learn it. But this object is huge, and our learning algorithm needs to be efficient, so it cannot really do it. So what it can only do is to learn the properties that we need. So if we want an indistinguishable model, it knows what the distinguishers are, and it only learns the properties that the distinguishers check. So if we want to keep the degree distribution, then it needs to learn the degree distribution. If we want to keep edges across the cut, it needs to learn the edges across the cuts that it checks. But sometimes we might want more properties that cannot be verified by the distinguisher, which is efficient algorithm. So suppose we know something. We know that the graph has a uniform degree. Then it would only make sense we want to also generate a graph with a uniform degree. Or we know that this graph has so many edges. So we might want to generate this graph that also has the same number of edges. So this property was already suggested in GGN that talked about generating random looking object, where they called it truthfulness, which is that we want to enforce some additional property that cannot be verified. So we also use this, their formalization, and we use this property, and we also want to sometimes keep some additional properties that we know. And these properties cannot be learned and also cannot be verified, so we assume these are properties that we know. So now I can talk about a problem setting. So we have a huge object and a set of distinguishers and some truthfulness requirements sometimes. And then our goal is to learn this huge object and then output a model that can generate this G prime that is indistinguishable from G. So are there any questions about the model? Okay.
Sorry, I didn't fully get the truthfulness part. Could you say that one more time?
So if we want...
Something we can check, right?
It is something we can check. So suppose you know your original object has uniform degree, then you might want to generate a uniform degree graph, but you can never verify it if you just receive samples, because you're never going to read this entire object. So this is the like enforcing some additional properties.
And the truthfulness is with respect to particular pre-specified property?
Yeah, they have to be pre-specified. Yeah, because we cannot learn them, so we have to know them ahead. Okay, so this is our setting. So now, before I'm going to talk about our results, I'm going to talk about how this connects to different areas, because this has a lot of connection. It also brings up a lot of questions about this connection to different areas. So I started with generative models. So there are works that are trying to imitate a specific object. For example, trying to create graphs that have the same degree distribution as the graph representing the internet network. And it is also connected to GANs, in which the idea is to generate a distribution that is similar to a different distribution by an iterative process in which the distinguisher tries to differentiate between the suggested model and the original distribution. And then this output of the distinguisher is used to update the model. We are different from the setting of GANs that we're trying to imitate a specific huge object and not a distribution over small objects. But we also have this idea of a distinguisher, and we're trying to get an indistinguishable object. So also, I've already mentioned the work of Goldach, Goldwasser, and Nissenbaum, that they discussed this generative huge object in the pseudo-random setting. So they don't have a learning part, but they do have two things that we're using from their work. One of them is this additional truthfulness condition. And the second is that we need also an efficient implementation, because we are also generating something that's supposed to represent a huge object but needs to be small. So in the case that our object is a graph and that our distinguishers check the number of edges across a cut, this is similar to the setting of the regularity lemma. So the regularity lemma was introduced by Samaradi, and the idea is that you can take any graph and partition its set of vertices such that the induced graph between every two sets is more or less uniform up to an error. Now, this is an inefficient process, but there have been subsequent work, one of them by Travis and Tulsiani and Vadam, that also show that this weaker version of the regularity lemma can be achieved efficiently. And we are going to use the regularity lemma so in this case. And there is another connection to the fairness literature. So in algorithmic fairness, the idea is in many times to learn some function that's going to be accurate, but also is not going to, it's going to protect some certain subgroups. And the idea of outcome indistinguishability that we're using here was introduced in order to keep these properties so a distinguisher could verify that the learned function is not, is protecting this subgroup. And we're using the same setting to achieve a goal which is not fairness, but like to define what our generative model means to be accurate. So now I'm going to talk about our results. So the first thing we're doing in this work was to introduce this idea of trying to create generative models for huge objects. And then we show that in some settings, existing learning algorithm and existing boosting algorithm works as they are, even in the huge object setting. In different situations, they don't work, and then we need to do more work. And I'm going to talk about two such settings. One of them that we have some truthfulness requirement, which is not trivial. And the other one is that we're handling a sparse object, in this case, a sparse graph. So I'm going to start with the first. So in the first result, our object is a huge function, a huge binary function. So it is represented by a truth table of length 2 to the n. And our distinguishers check for the expected value of a function on some sets. So for example, this D1, it checks for the expected value across this set. And if f and f prime are indistinguishable with respect to D1, it means that they have more or less the same expectation on the set that D1 checked. And for D2, this is the same. And what we want is to keep the number of ones in the function. So if the original function, we know it has exactly m ones, we want our model to also satisfy this property. And what we're showing that if this collection of distinguishers is learnable, which I'm going to explain in the next slide, then we can do it. So how do we do it, and what do I mean by being learnable? So if we didn't have this additional truthfulness requirement, then existing boosting algorithm works if the set is learnable. And what I mean by learnable is that if there exists some D which can tell apart f and f prime, then we can efficiently find it. So, and then the algorithm works in a very straightforward way. If there is a D which tells apart f and f prime, we can find it, and then we use its output to update f prime. And what this work shows is that this process is going to end up really quickly and going to output f prime, which is indistinguishable. But in this case, we're not promised anything about the number of ones in the function. If we wanted to keep the number of ones, but we didn't need to learn anything, this is the setting in GGN when they try to create a random function that has a fixed number of ones. And what they're doing, they're dividing the set of possible inputs, the 0, 1 to the n, into a tree, such as every node in the tree represents some subset of inputs. And they assign budget to each node in the tree. And the way they assign budget, there is a closed form to how the budget look for a random function. So they can exactly know what budget to put at every node in the tree. What we're doing in this work is combining these two settings. But because in our case, we only learn an approximate f, we don't really know what the right value to put in every node in the tree. So we have some error, and this error grows as we go down. So when we are in the top of the tree, the sets represented are large, and the error is small, and that is manageable. And when we go down in the tree, we need to do a less efficient argument that's going to have a smaller error to prevent our error from exploding. So in a high level, this is what we're doing in this setting of where we have an interesting truthfulness condition. And now I'm going to talk about graphs. So now we have a huge object that needs a graph. And our distinguishers check for the number of edges crossing a cut. So it accepts if an edge crosses the cut. And there are two natural ways to access a graph. One of them is by receiving an adjacency symmetric access. So if you receive uv1, then n1, or uv2 and 0, because there is no edge. And then the distinguishers verified the number of edges crossing a cut up to an error which scaled with the number of vertices squared. So we already see that this is only reasonable in the case of dense graphs, because if the number of edges is v, then the error is huge. And in this setting, standard boosting algorithms work. We might want to receive a random edge, which is making more sense if the graph is sparse, because in the adjacency matrix, we're just going to receive 0 all the time. And then the set of distinguishers checks for the fraction of edges across a cut. And if the graph is dense, there isn't really a huge difference between these two methods, because what we receive is more or less the same. If the graph is sparse, then the second one is the only one that makes sense, but also standard algorithms don't work, because their error scales with the number of vertices squared. So before I'm going to say what we're doing, I'm going to sort of give an intuition why sparse objects are different from dense ones. So first of all, it's interesting to learn sparse objects, because if we imagine a graph representing, say, a social network, then it is making sense that this graph is going to be sparse. But somehow these objects are harder to learn. We can look on a binary function as a dense object, because sort of what we care of, f of x, is dense in its set of options. And we can look on a function that has a large range as a sparse object, because what we care about now, f of x, is still of size 1, but now its domain is huge. And in the first case, standard boosting algorithm works. In the second case, we can only handle it with respect to a very limited set of distinguishers, which is less interesting, and I'm not going to discuss it. And also in the case of graphs, what we care about in graphs is the set of edges. And for a dense graph, this is comparable to the domain, which is v squared. And in sparse graph, this is now very small comparing to it. And another problem is, if we want to generate random samples, that we cannot do rejection sampling, which is normally the standard way to generate random samples. This is because the way we do rejection sampling is we sample, say, 2 vertices, query if there is an edge, and if yes, we output this edge. And this is not going to work in sparse graphs. So there are some difficulties, and we can handle them for only a specific class of sparse graph, not for all graphs. So the graph we can handle are those that don't have a very dense subgraph. So like this sparse graph cannot have a square root n vertices clique, or any graph which is similar to a square root vertices clique. And many graphs which are sparse are more or less uniform. Random graphs have this property, but also any graph that doesn't have this like super dense subgraph. And again, the set of distinguishers that we care about are those that are edges across a cut. So what we show in this part is that if this collection of distinguishers is learnable, then there exists a model which outputs a dense graph that is indistinguishable from our huge object. And the way we do it is by looking at this dense graph, and looking at our input graph, which is a sparse graph, and realizing that there exists a dense graph that is indistinguishable from that, because this graph has no very dense subgraphs. And then we sort of pretend that we learn the dense graph that is indistinguishable. And we know that this exists from the strong irregularity lemma that does not have an efficient algorithm, but I mean, it's an existential property. And then we learn this dense graph that is indistinguishable from our input graph, and we output a dense object. And this is only working because what we actually care is the fraction of edges crossing a cut. And the reason we need to output a dense object is because we are doing rejection sampling, and we cannot do it for a sparse object. So this is what we can do for dense graphs. Sorry, for a sparse graph, and we output a dense graph. Yeah. So now I'm going to discuss some open questions. So what we view our model is like a first step in this idea of trying to generate huge objects. And there are a lot of different questions that are very interesting, and also if someone wants to discuss it later, they can contact me. So one of the things that's, like we only discussed here a graph and function, and there are more objects that it's possible to do. We only try to achieve the really basic object in theoretical computer science. And also, can we handle more sparse objects? For example, can we handle like a function which has a large domain? Can we handle a larger class of sparse graphs? In general, sparse objects are harder, but I think this point of view of outcome and distinguishability sort of formalizes in a very concrete way what we want to achieve. And I hope it's going to help to be able to handle more sparse objects. And can we output a larger set of distinguishers, specifically those that are not an average across a set, but like have some interaction? For example, if a distinguisher checks for a triangle, then it requires a very different type of model, because now we have dependency between these edges that we didn't have in the case that we're only checking for a number of edges across a cut. So can we have also these kind of questions? So this is the open question that I have to say, and thank you. Are there any questions?
How much of the challenge for sparse objects comes from the need for a learning algorithm versus, say, wanting just a kind of a low complexity model that you don't necessarily learn from samples?
I think sort of the difficulty is in both. And I mean, even the rejection sampling part, which seems like a really technical problem, right? We have the object, why can we handle? It's really hard to figure out a different way to, so I think the difficulty is in both, both cases, yeah.
So the way that you set up the graph version, you view it, I guess, as the distinguishers are testing for quadratic forms with the Laplacian matrix, right, which is the same as measuring like a cut of, if you take the quadratic form of some indicator.
When we receive a random edge, we receive adjacency matrix entry.
If the quantity that is a cut of a particular
yeah.
subset of edges, right, is sum is a quadratic form with this matrix. So I was wondering, is there a way to set this up that just operates on matrices without all of the graph language, where the huge object is a matrix, and you're trying to produce, I guess, you're trying to model this matrix in a way that agrees on some subset of queries that are quadratic forms or something like that?
So the view of like an adjacency matrix, I suppose, is similar to that.
Right.
Yeah, so I think for at least in the part that we looked on, for dense graph, it doesn't matter how you view it. And like for sparse graph, the matrix view is not like, it's hard to work with it because it's practically zero. Or at least it's indistinguishable from zero.
But in the dense case, kind of, at least in principle, it could be just some other matrix that's not the adjacency matrix of a graph, but just a matrix.
Yeah, we didn't, at least in the set of distinguishers we handled, there didn't seem to be a difference, but I mean, different set of distinguishers might, have another matrix, which is more helpful.